You take an electron from your body, another from a star that died 3 billion years ago, a third from the Large Hadron Collider in Geneva. Line them up, test them, measure their mass, their charge, their spin. Every single property matches. Not similar, identical. Zero difference. Not one electron in 10 to the 80th power atoms across the observable universe breaks this pattern. Same mass at 9.109 times 10 to the negative 31 kilograms. Same charge at negative 1.602 times 10 to the negative 19 coulombs. Same spin at 1/2, every electron, everywhere, always. But electrons laugh at this logic. A physicist at Princeton measured electron charge to mass ratios in 2023 with 0.5% error from the accepted value of 1.76 times 10 to the 11th coulombs per kilogram. Every measurement across every lab on every continent for over a century returns the same numbers. The Max Planck Institute in Germany calculated electron mass in a Penning trap using carbon-12 isotopes as reference. Result: one electron equals exactly 1 over 1,836.1526737 times the mass of a proton. 30 decimal places of precision, not approximate, exact. Graduate student. Late at night. Wheeler has an idea burning in his brain. He tells Feynman he knows why all electrons have identical charge and mass. Feynman asks why. Wheeler says, because they are all the same electron, one particle, moving backward and forward through time, threading through space-time like a needle through fabric. One electron creating the illusion of countless electrons by crossing the same moment in time multiple times. At any given instant, this particle appears in billions of locations simultaneously because it has traveled to that moment from different directions in time. Half the crossings move forward. Those are electrons. Half move backward. Those are positrons. The observation that positrons could be represented as electrons moving backward in time. This insight appears in his 1949 paper called The Theory of Positrons. Wheeler knew the theory had problems. If one electron bounces through time creating all electrons and positrons, we should see equal numbers of both. We do not. The universe contains vastly more electrons than positrons. Wheeler suggested maybe positrons hide in protons. Not convincing. Feynman calculated that this one electron would need to traverse space-time 10 to the 80th times, each journey taking 460 septillion years. Experimental lower bound for electron lifetime sits at 6.6 times 10 to the 28th years. The math breaks. Wheeler himself wrote in his memoir that he knew our corner of the universe has more electrons than positrons. But he found it exciting to think of trajectories in space-time, moving unrestricted in any direction. This script is researched and factual, using sources from Contemporary Physics Volume 46, published November 2005, by Yasser Omar at the Technical University of Lisbon, detailing indistinguishable particles in quantum mechanics, and the Journal for General Philosophy of Science. June 2020 article by Dennis Deeks on identical quantum particles as distinguishable objects, which rigorously examines the factorism, assumption, and symmetrization postulates in quantum field theory. Now back to the information. When two electrons approach each other, their wave functions overlap. After interaction, you cannot track which electron went where. The particles lose their identity, not because we lack precision in measurement, because identity itself becomes meaningless in quantum mechanics. You watch the red ball exit left, the blue ball exit right. Even if you paint them identical colors, you track their paths. You know which is which. Quantum particles do not have trajectories between measurements. Their wave functions describe probability distributions. Electron 1 has 50% chance here, 50% there. Electron 2 has the same distribution. They interact. The wave functions merge, then separate. You measure two electrons, but you cannot say which electron corresponds to which initial state. The question itself violates quantum principles. The swap cannot change observable properties. Measurements must return identical statistics, whether you call them electron 1 and electron 2 or electron 2 and electron 1. This seems trivial. It is revolutionary. Wolfgang Pauli formulated this in 1925 for electrons. He needed to explain atomic spectra, why helium with 2 electrons is chemically inert, but lithium with 3 is reactive, why electrons in atoms arrange themselves in shells. He proposed that no 2 electrons can share all 4 quantum numbers: principal quantum number, angular momentum quantum number, magnetic quantum number, spin quantum number. If 2 electrons occupy the same orbital, they must have opposite spin, one up, one down. Freeman Dyson and Andrew Leonard proved in 1967 that matter stability derives directly from this principle. This connection between spin and statistics is called the spin statistics theorem. Pauli published his seminal paper on this in 1940, titled The Connection Between Spin and Statistics. He showed that, assuming relativistic causality, particle spin determines commutation relations, whether fields commute or anti-commute, therefore whether particles obey Fermi-Dirac or Bose-Einstein statistics. For fermions, the antisymmetric wave function has stark consequences. Write the wave function for two identical fermions in the same state. Apply the antisymmetry requirement. Swap the particles. The wave function must equal negative itself. But swapping identical particles in identical states changes nothing. The wave function also equals itself. The only function equal to both itself and negative itself is 0. The wave function vanishes. The state cannot exist. Two identical fermions cannot occupy the same quantum state. This is the Pauli principle derived from pure symmetry. Created single electrons from two separate sources in identical quantum states. Used a two-dimensional electron gas in gallium arsenide. Confined electrons to one dimension using strong magnetic fields. Applied voltage pulses to emit single electrons. Billions per second, 1 electron per nanosecond. Set the electrons to an electronic beam splitter. Observed quantum interference. The electrons showed anti-bunching. They avoided meeting in the same output arm. Classical particles show no such preference. This anti-bunching proves indistinguishability. The electrons interfere quantum mechanically. Fev stated that some minimal environmental interaction occurred, preventing complete indistinguishability. Perfect indistinguishability requires complete isolation from environment. But the experiment showed high degrees of coherence. Future work aims for total indistinguishability to enable electron entanglement violating Bell inequalities. When energy pumps into the field, it creates a stable propagating excitation. That excitation manifests as what we call an electron. Electrons work similarly. There's one electron field filling the universe. Every electron is a vibration in this single field. The field has intrinsic properties, a characteristic frequency, a rest mass, an electric charge, a spin. These properties belong to the field, not to individual excitations. When you measure an electron, you measure the field's properties. Every measurement returns the same values because every electron is the same field vibrating. 8 gluon fields exist, one for each gluon color charge. The universe is not made of particles. It is made of fields. Particles are what we see when we probe these fields. Spin half emerges from the field's transformation properties under rotations. The field itself is immutable, indestructible, fills every point in space-time with the same value. Quantum fluctuations within the field are coherent across the entire universe. This provides the ontology for quantum weirdness. Wave functions represent the reality of these universal quantum fluctuations. Proceedings of the National Academy of Sciences published research on indistinguishability-enabled quantum coherence for metrology. Team demonstrated how particle indistinguishability supplies unique contributions to quantum coherence. Tested fermionic and bosonic statistics using photonic systems. The experiment used spontaneous parametric down-conversion to create photon pairs. Applied optical compensation to simulate fermionic exchange phase. Observed that the pi exchange phase causes the wave function on symmetric states to vanish. This mirrors Pauli exclusion for real fermions. Multiple occupations of the same state become forbidden. The destructive interference from exchanging identical fermionic particles in superposed two-particle states creates both Pauli exclusion and the observed photonic vanishing. Future scalability requires deterministic single photon sources. Quantum dots as electron sources. Initialized spin states, quantum point contacts as electronic beam splitters, atomic circuits to control single electrons. Indistinguishable electron production verified by Gwendal Fev's team. In PNAS May 2022 article on activation of indistinguishability-based quantum coherence, showing experimental confirmation that fermionic exchange phases enforce Pauli exclusion through destructive interference in controlled photonic analogs of many-body fermion systems. Now back to the information. The mathematics of quantum field theory treats particles as operators. Creation operators add excitations to the field. Annihilation operators remove them. For bosons, these operators commute. You can create two photons in any order. The result is the same. For fermions, the operators anti-commute. Creating two electrons in states A then B gives negative the result of creating them in states B then A. This anti-commutation builds anti-symmetry into the mathematical foundation. The formalism automatically enforces indistinguishability and exclusion. The determinant's mathematical properties ensure anti-symmetry. Swapping two particles exchanges two rows. Determinants change sign when you swap rows. Perfect anti-symmetry emerges. If two particles occupy the same state, two columns become identical. Determinants with identical columns equal 0. The exclusion principle falls out automatically. His paper introduced what became known as Slater determinants, after John Slater used them extensively. Dirac wrote that an antisymmetric eigenfunction vanishes identically when two electrons occupy the same orbit. The statement is both mathematical and physical. The math requires antisymmetry. The physics forbids double occupancy. They are the same requirement viewed from different angles. The VIP experiment at Gran Sasso tests Pauli exclusion by searching for forbidden transitions. If exclusion were slightly violated, electrons could occasionally jump to already occupied states. These transitions would emit X-rays shifted in energy by about 300 electron volts. Silicon drift detectors monitor for these signals. Decades of searches find nothing. Upper limits on violation probability sit at 5 times 10 to the negative sixth. The exclusion principle holds to extraordinary precision. The statistical distributions match theoretical predictions exactly. Composite particles follow statistics determined by their constituent fermion count. Even numbers of fermions create bosons. Odd numbers create fermions. Helium-3 has 2 protons, 1 neutron, 2 electrons. 5 fermions total, odd count. Helium-3 is a fermion. Below 2.6 millikelvin, it forms Cooper pairs. Paired fermions act as composite bosons. Helium-3 transitions to a superfluid state. Helium-4 has 2 protons, 2 neutrons, 2 electrons. 6 fermions. Even count. Helium-4 is a boson. It becomes superfluid at 2.17 Kelvin without pairing. Direct Bose-Einstein condensation. The phenomena validate indistinguishability on observable scales. The team blasted 5 electrons off a carbon atom, left 1 electron with a nucleus, carbon ion with charge plus 5, set it racing in the trap, measured the revolution frequency. Electrons have spin, act like tiny magnets. In strong fields, this spin precesses, wobbles like a gyroscope, extremely rapid wobbling. But the revolution frequency and wobble frequency lock into an exact ratio. Quantum mechanics creates a gear mechanism, links carbon ion mass firmly to electron mass. The unknown gear was the G factor, the gyromagnetic factor. Unimaginable precision. Stated in kilograms, electron mass equals about 10 to the negative 30 kilograms, 30 zeros after the decimal point. The electron is a lightweight, but plays a heavyweight role in nature. This consistency across space and time points to something fundamental, not a coincidence of manufacturing, not a stable equilibrium among forces, a property of space-time itself. A way to calculate forces without action at a distance. Quantum field theory promotes fields to physical reality. The primary reality, particles become secondary, derived, emergent. The excitation carries charge. The field transforms under rotations in a specific way. The excitation acquires spin. All electrons have the same properties, because all electrons are the same field having the same properties. Leibniz's principle of the identity of indiscernibles states that no two distinct things can have all properties in common. Electrons violate this principle. They have all properties in common, yet we treat them as many particles, not one. Some philosophers embrace the field view, abandon particle language entirely, talk only of field excitations. Others resist, argue that practical physics still treats electrons as countable objects. We say there are 2 electrons, not that the electron field has 2 excitations. The language matters less than the math. The math is clear. Indistinguishability is fundamental, not just symmetric or antisymmetric. Arbitrary phase shifts, these anyones appear in quantum Hall effect systems. They are quasi-particles, not fundamental particles, emergent phenomena in condensed matter. But they demonstrate that statistics is richer than the fermion-boson dichotomy in lower dimensions. In 3-dimensional space, only fermions and bosons exist. Parastatistics are mathematically possible, but nature does not use them. Quarks were once proposed as paraparticles. This suggestion helped develop quantum chromodynamics. Quarks turned out to be regular fermions, with an extra quantum number called color charge. Wolfgang Pauli in his Nobel lecture noted he was puzzled by the principle. Already in his original paper, he stressed that he could not derive the exclusion from basic quantum principles. He postulated it as an independent principle. Later work by Pauli and Marcus Fiers in the late 1930s made progress. Pauli's 1940 paper proved the spin statistics connection using relativistic quantum field theory. The exclusion principle for spin-half fermions follows as corollary. Many physicists tried to skip relativity, find proofs using ordinary quantum mechanics alone. Spin itself is a relativistic concept. No fully satisfactory non-relativistic proof exists. The connection requires special relativity and quantum mechanics together, quantum field theory. The VIP3 experiment at Gran Sasso runs continuously, searching for anomalous X-rays. Statistical weight of forbidden Pauli-violating states has upper limit at 5 times 10 to the negative sixth. 0 observed violations over years of data. Other experiments test Bose-Einstein statistics. Photon bunching in lasers, Boson behavior requires identical particles in symmetric states. Every photon in a laser beam occupies the same quantum state. Same frequency, same direction, same phase. This coherent light proves bosonic statistics and indistinguishability. Entanglement requires indistinguishability. For quantum networks, single photon sources must emit identical photons. Quantum dots as sources have rich, solid-state environments. These environments create distinguishability, decoherence, noise. Engineering sources to produce truly indistinguishable photons is a major research focus. Hong-O-Mandel interferometry tests photon indistinguishability. Two photons enter a 50-50 beam splitter from different ports. If perfectly indistinguishable, both exit the same port. Bunching. If distinguishable, they exit different ports some fraction of the time. The dip in coincidence detections quantifies indistinguishability. Modern quantum optics labs measure Hong-O-Mandel visibility above 99%, near-perfect indistinguishability. Condensed matter physics depends on Fermion statistics. Band structure in solids, electrical conductivity, semiconductors, superconductivity, all derive from Pauli exclusion and indistinguishability. In metals, huge numbers of electrons occupy molecular orbitals forming continuous energy bands. Strong conductors have electrons so degenerate they barely contribute to thermal capacity. The electrons fill energy states up to the Fermi level. All lower states occupied. Pauli exclusion prevents further filling. This creates Fermi seas, Fermi surfaces. The geometry of these surfaces determines electronic properties, magnetic properties, optical properties, chemical properties, all consequences of exclusion. Shell models for nuclei directly parallel atomic shell models. Magic numbers in nuclei: 2, 8, 20, 28, 50, 82, 126. These are closed shells, extra stability, analogous to noble gases in chemistry. The physics is identical. Fermions, filling states, exclusion preventing overfilling, indistinguishability allowing anti-symmetric combinations. Statistical mechanics needed overhaul after quantum mechanics. Classical statistics assumed distinguishable particles. Each particle has identity, labeled, tracked. Counting states meant counting all permutations of particles among energy levels. Quantum mechanics forbids this. Identical particles mean only occupation numbers matter. How many particles in each state, not which particles. For n particles in n states, classical counting gives n factorial arrangements. Quantum mechanics divides by n factorial for bosons, removes permutations that represent the same physical state. For fermions, occupation numbers are 0 or 1, each state either empty or filled. The division by n factorial is automatic in the formalism. Classical ideal gas entropy formula included a term proportional to n log n. This makes entropy non-extensive. Doubling system size and particle count does not double entropy. Thermodynamics requires extensivity. Mixing two identical gases should not change entropy. Classical statistics says it does. Quantum statistics solves Gibbs' paradox. Dividing by n factorial fixes the entropy formula. Extensivity follows naturally. Indistinguishability removes the paradox. These structures are reproducible because atoms of the same element are identical, not statistically similar. Identical. A biological enzyme has thousands of atoms. Precise arrangement matters. The arrangement works because atoms are interchangeable. Swap 2 carbon atoms in a protein, nothing changes. The protein folds the same way, functions the same way. Life depends on this indistinguishability. Every atom in a crystal lattice is identical to others of the same element. The lattice symmetry, the electrical properties, the optical properties, all rely on atomic identity. Diamond has brilliant sparkle because carbon atoms in diamond structure scatter light identically. Conductors conduct because electrons hop between identical atoms. Every hop encounters identical environment. Band structure calculations assume this. Solve for one unit cell. Extend to entire crystal via translation symmetry. Works because atoms are indistinguishable. Transistors, integrated circuits, computer chips, all rely on this at the atomic level. Billions of transistors on one chip. Each functions identically to others. Not just good manufacturing. Fundamental quantum mechanics. Each emitted photon has identical energy, direction, phase to the triggering photon. The photons are indistinguishable. They interfere constructively. Amplify. The laser beam is a macroscopic quantum state. Countless identical photons. Coherent. This coherence is not engineered. It is enforced by Bose statistics. Photons prefer to occupy the same state. Bunching tendency. Lasers exploit this natural preference. Bose-Einstein condensation takes this further. Cool bosonic atoms to near absolute zero. Below critical temperature, all atoms collapse into the same ground state. One macroscopic quantum wave function. Thousands or millions of atoms acting as one. First achieved in 1995 with rubidium-87 at Gila, temperature around 170 nanokelvin, 20 million atoms condensed. The condensate displayed interference patterns, matter wave behavior on macroscopic scale, direct proof of indistinguishability, every atom in identical state. Wave functions perfectly overlap. Why are particles excitations of fields? Why do fields fill space-time? Why do identical particles exist at all? Physics describes how, not why. The equations work. Predictions match experiment. Understanding accumulates. But the bedrock question of why space-time hosts quantum fields rather than classical particles, that question sits beyond current physics. Maybe string theory provides answers. Maybe quantum gravity. Maybe some future theory we have not imagined. For now, we observe, we measure, we calculate, and we find that electrons are indistinguishable to extraordinary precision. Electrons from an electron gun in a helium-filled tube. Accelerating voltage held at 201.3 volts. Current varied from 1.3 to 1.7 amperes. Measured beam radius photographically. Derived EM ratio as 1.85 times 10 to the 11th coulombs per kilogram. Bounded between 1.44 and 2.23 times 10 to the 11th. Compared to accepted value of 1.7588 times 10 to the 11th. Excellent agreement. Every lab everywhere conducting this measurement gets consistent results. The electron charge to mass ratio is a universal constant. Not variable, not approximate, constant. Calculated masses. Every electron matches expected mass. 0 exceptions. Positrons match electron mass exactly. Antiparticle of electron. Opposite charge. Same mass, same spin. Indistinguishable from each other. Electron-positron pair production from high-energy photons. The Dirac field excites. One excitation forward in time is electron. One backward is positron. Both are the same field vibrating. Properties identical except charge sign. Quantum electrodynamics, the quantum field theory of electromagnetism, is the most precisely tested theory in physics. Anomalous magnetic moment of the electron predicted by QED matches experiment to 10 significant figures. The agreement between theory and measurement is staggering. 1 part in 10 billion. This precision validates the quantum field theory approach, electrons as field excitations. Indistinguishability baked into the mathematical structure. Research published in 2022 at PNS showed how to control and exploit this. Build quantum gates using particle exchange. Topological quantum computing proposals rely on this. Anyone's in two-dimensional systems. Braiding world lines creates computational operations. Fault-tolerant by design. Decoherence resistant because information stored in global topology, not local degrees of freedom. Creating and manipulating indistinguishable particles on demand. Single photon sources with high indistinguishability. Single electron sources likewise. Quantum dots show promise. Emit electrons with controlled energy and spin. But environmental coupling creates distinguishability. Phonons, electric field fluctuations, impurities. Each interaction marks the particle. Breaks indistinguishability. Researchers engineer ultra-pure materials. Cryogenic temperatures, shielding from electromagnetic noise, push indistinguishability metrics higher. Hongwu-Mandel visibility improves year by year, from 90% to 99% to 99.9, asymptotically approaching perfect indistinguishability. Quantum computing requires indistinguishable qubits for gate operations. Quantum sensing exploits interference of indistinguishable particles for measurement precision beyond classical limits. The field is active, progressing, driven by fundamental physics that is rock solid and tested exhaustively. Both occupy the 1's orbital, spin up and spin down. Second row begins. Lithium has 3 electrons, 2 fill the 1's. Third goes to 2's, higher energy, farther from nucleus, less tightly bound. Reactive. The pattern continues. Every element's chemistry follows from electron configuration. Configuration determined by exclusion, exclusion enforced by anti-symmetry, anti-symmetry required by indistinguishability. The entire structure of chemistry rests on electrons being identical fermions. Fluorine is highly reactive because 1 electron short of filled shell. These are not averages, not tendencies, absolute rules. Identical particles create identical behavior. The bond is not 2 atoms each contributing 1 electron. The bond is 2 atoms sharing 2 indistinguishable electrons. Molecular orbitals extend over multiple nuclei. Electrons delocalized, wave functions overlapping. This delocalization enables electrical conduction in conjugated molecules, electron transport in biological systems, photosynthesis, cellular respiration. Electrons hop between molecules. Indistinguishability permits this hopping. Each site is equivalent for electrons. Created when energy pumps in, annihilated when energy drains out. But the field itself persists, and the field has one set of properties. Every excitation reflects those properties identically. Predicts new particles later discovered. The Higgs boson, top quark, tau neutrino, all predicted by quantum field theory, all found. Every major particle physics discovery in the last 50 years came from quantum field theory calculations. But for the physics we can test, quantum field theory delivers, and at its heart lies indistinguishability, the symmetrization postulate. Fermions antisymmetric, bosons symmetric. This simple rule generates the richness of the material world. Every atom, every molecule, every material property, every chemical reaction, every biological process, all follow from indistinguishable quantum particles obeying exchange statistics. Recent research pushes boundaries. Gravitational wave detectors like LIGO use laser interferometry. Indistinguishable photons enable precision measurement of space-time distortion. Each photon in the laser is identical. Interference pattern shifts by tiny fractions from gravitational waves. Detection requires stability. Identical photons provide that stability. Inconsistent photons would create noise, mask the signal. Only indistinguishability permits the measurement. Voltage pulses on gate electrodes emit single electrons on demand. 1 per nanosecond, billions per second. These electrons route to beam splitters made from quantum point contacts. 2 input channels, 2 output channels. Indistinguishable electrons entering different inputs show anti-bunching. Both exit the same output. Distinguishable electrons show no preference. Classical statistics predict 50% in each output. Quantum mechanics with indistinguishable fermions predicts 0 in mixed output, 100% in bunched outputs. Experiment confirms quantum prediction. Anti-bunching proves indistinguishability. The negative sign from antisymmetry causes destructive interference for fermions trying to bunch. Pauli exclusion emerges from interference, not a separate principle, a consequence of wave function symmetry and indistinguishability. Upper limits keep dropping, precision keeps improving, confidence increases, not because we believe the theory, because we test it and it passes. Within 2% of modern value of 1.602 times 10 to the negative 19. Given the experimental challenges and technology of 1910, this agreement is remarkable. It showed electron charges quantized. Every electron carries the same charge. No partial charges observed. This quantization was puzzling at the time. Quantum mechanics had not been invented. Now we understand charge is a property of the electron field. Quantization reflects the field's discrete excitations. Consistency across different measurement methods. Different labs, different techniques, all agree. The fundamental constants are constant, not varying in space, not varying in time. Constant across the observable universe and throughout its history as far as we can test. The field is universal, therefore properties are universal. Therefore particles are indistinguishable. Superconductivity arises from electron-Cooper pairs. 2 fermions binding creates composite boson. Below critical temperature, Cooper pairs condense. Macroscopic wave function. 0 electrical resistance. Supercurrent flows without energy dissipation. This phenomenon is quantum mechanics on visible scales. Current in superconducting rings persists for years, decades, no decay. Quantum coherence maintained macroscopically. Possible because Cooper pairs are indistinguishable bosons occupying the same quantum state. Without it, superconductivity could not exist. Without identical atoms, no coherent macroscopic wave function, no superflow, no quantized vortices, no second sound. All these unusual properties stem from quantum mechanics scaled up. Predictions of element abundances match observations. Success validates quantum statistics. Those fluctuations evolved into galaxies. Without quantum mechanics, without indistinguishability, the universe would be featureless. Same charge, negative 1.602 times 10 to the negative 19 coulombs. Same spin 1/2. 0 exceptions found despite century of searching. Each type comprises indistinguishable members. In 1940, John Wheeler asked Feynman why all electrons have the same charge and mass. Wheeler proposed one electron moving through time. He was wrong about the mechanism, but right about the question. The answer from quantum field theory is that electrons are not separate entities. They are manifestations of one underlying field. The field has one mass, one charge, one spin. Every excitation reflects these properties. That is why electrons are identical, not because they are the same electron, because they are the same field.